Okay, we'll give it a minute.
Okay.
Yes, you know, people are always a little slow at coming in, and we recorded because there's a lot of asynchronous viewing, you know, because we got people in so many different time zones and stuff. So
yeah.
So yeah, we've stayed a couple of times at this little town in North US called Lahmati, and they've got lights on some buildings and on the little hill by the bay there to show where the ocean is expected to be in 2050. Like, yeah, oh, this town is not going to do well.
We should, maybe every town should have that if they're along the coast. Yeah, that's probably a visceral reminder.
Yeah, no, I couldn't figure out what was going on, and then I talked to one of the locals, and they go, "Oh, well, that's this." Like, ooh, now that's what I call awareness. Okay, let's go ahead and get started. I'd like to welcome Rob Skarbek. He's from the Lamont Doherty Earth Observatory. We don't hear about Earth observatories very often here. And he's applied to join us as a research scientist. And Rob, why don't you tell us a little bit about your background and then go ahead and start your talk.
Sure. Well, first of all, I'm really excited to have that opportunity to join you all. But most of my research has revolved around subduction zones in one way or another. Done a lot of work studying the earthquakes on subduction zone plate boundaries. And I've also done a lot of work studying porous media compaction. So how sediments that get subducted compact and drive fluid flow. And right now I have a project studying snow compaction to try to understand how snow compacts into ice at the tops of ice sheets. Very recently, I've gotten involved into a kind of nascent project to do some modeling of how icy plates might be subducting on Europa.
Cool.
But am I coming through?
Yes.
Okay. Okay. I'll start sharing. But today I have a fault mechanics talk for you. So I'm going to talk about friction, and particularly the rate and state friction equations, because it's very central to the fault mechanics modeling that I do. So I have some nuts and bolts slides, and then I'm going to talk about shallow moonquakes and show some kind of demo simulations that I've put together for this talk. And then at the end, I'm going to briefly talk about friction and faults in icy shells. Okay, so I like to just get into things. I study the motion of faults and other sliding surfaces, and I do this by collecting and analyzing friction data and studying how material that is surrounding a fault influences a fault's motion, and also studying tectonic and tidal stresses that drive motion. So the equation at the top of this slide is kind of embodies all of the research that I do. So if you think about a fault or any kind of sliding surface, like say at the bottom of an ice sheet or a glacier, then you can say that the motion on that fault is controlled by the balance of shear stresses that's represented by this equation. So there are stresses that promote sliding from tectonics or tidal loads, and also the stress caused by elastic or viscoelastic deformation in the material around the fault. And there are stresses that resist sliding, mainly friction, or some combination of friction and viscous flow if the temperature is high enough, and also inertia. So really kind of all my work goes into studying these different stresses and then using this stress balance equation to do simulations of fault motion. So let's get into talking about friction. Rate and state friction. My favorite way of introducing rate and state friction, and I feel like it is probably somewhat unfamiliar topic for this audience, is to talk about how people do friction experiments. So the most common way to measure rock or ice friction is to use what's called a biaxial deformation apparatus. So that's shown here in the schematic. And that basically consists of a piston that can apply a force vertically and another piston that applies a force horizontally. And then a sample gets kind of sandwiched between these two pistons and placed under a horizontal load. So in this cartoon, the sample is a piece of ice in the middle, and it's sandwiched between two rock samples. And then the vertical piston drives that center block at some type of prescribed velocity, and the resulting stresses are measured, and then the friction coefficient is the vertical stress divided by the horizontal stress. So that's a measure of the friction on the surfaces between the center block and the side blocks, or sometimes people put some kind of fault gouge in there. And this setup works very ideally because the area of contact along those surfaces doesn't change because the center block is longer than the side blocks. So people do these, there's three kind of different protocols people do. They do velocity steps where they move the center block at some velocity and then abruptly step it to a new velocity. And that provides information on how the friction coefficient depends on the sliding velocity. Another common test is called a slide hold slide test, where the center block is moving and then stopped altogether and then restarted again. And then that provides a measure of how much frictional healing takes place when there's no sliding going on. And it's also a measure of the static friction coefficient. And so recently I've been working with a colleague of mine, Christine McCarthy at Lamont, and we've been trying to understand how the frictional properties depend on oscillating stresses, which mimic tidal stresses. So in those experiments, we oscillate the driving velocity of that center block about some mean value and then study the frictional response. So this is an example of some actual data. This is ice on rock friction data. In the center panel is showing a sequence of velocity steps and slide hold slides. And usually people plot the friction coefficient against the total displacement that has occurred. So there's a sequence of velocity steps over, the velocity is ranging from 1 to 100 microns per second in the middle of that center panel. And then there's a sequence of hold slides on the right side. So I'm going to focus on velocity steps because that's kind of like the canonical thing of rate and state friction. So the top inset's showing what a velocity step response looks like. So the sliding velocity, when the sliding velocity gets increased, there's a big spike in the friction, and then like an exponential decay to a new steady state value at the new sliding velocity. And so in general, that kind of response is ubiquitous for essentially any material that anybody's ever tried to do one of these experiments for. So this plot is showing velocity step responses for granite, soda lime glass, acrylic plastic, Teflon on steel, and wood. And so these types of measurements, people started doing about 40 years ago, and trying to understand this nonlinear response is what led to the rate and state friction theory. And so before I show you that, like the equations of that theory, I just want to show some of this oscillation data that Christine and I have been looking at. So this is ice on rock data again. And so in each of these panels, the gray curves are showing the applied velocity oscillations. And the black curves are showing the measured frictional responses. So again, the oscillations and the applied velocity are kind of like a proxy for applying an oscillating shear stress to the sliding surface. I'm going to zoom in on one of these panels, but if you look closely, you might notice that the peaks in the friction response are not in phase with the peaks in the applied velocity response, which is some kind of an important thing that we've been seeing. So I'm going to zoom in on this panel. So this was an interesting experiment because and again, the black line is the frictional response to the applied velocity response in gray. The velocity oscillation induced kind of a slip event in the sliding surface. So over one period of this velocity oscillation, there's measured friction, and that's an indication that the sample has slipped very quickly. And also, you notice that this slip event takes place just before the peak forcing velocity, so just before the peak applied shear stress. And so that reflects a general characteristic that is important for any fault that's experiencing a tidal stress, that slip events don't necessarily take place during the peak tidal stress. So this is an example of this type of behavior in the real world, except not for a fault, but for the sliding surface at the base of an ice sheet in Antarctica. So in Antarctica, there's a number of ice streams that discharge ice into the ocean, and they're essentially rivers of ice within a larger ice sheet. And so they're bounded on their margins by shear zones. And they're typically moving at speeds of like a few hundred meters per year. So like a lot of ice gets ejected into the ocean this way. Most ice streams in Antarctica move kind of like at a continuous rate, but there's one called the Whillans ice stream that is located at this yellow square on the map of Antarctica at the bottom here. And this ice stream moves via 2 stick slip events per day. And those events appear to be triggered by the ocean tides. So in both of the panels on the right, you are looking at the ice velocity in blue and the sea height as a gray dashed line. And so the upper panel is the actual observations. So there's one sliding event, usually during or after the high tide, and then there's another at low tide. And then the bottom panel is a result of a simulation that uses some ice rock friction data along the base of the ice sheet to try to reproduce that behavior. And it did a pretty good job. So, yes,
Rob, I just trying to get a physical handle on some of this. So when there's a slip event that occurs, is that because there's some sudden change in the mechanical properties of one material at the interface that is then removed and results in more contact, and then things kind of jam up again, or you get more friction again? What's the nature of that mechanically?
I think the nature, it's not that there's material properties actually changing on the bed, although some people might think it's ice pressure changing, or not ice pressure, the water pressure at the base of the ice sheet changing. But it may also just be from strain accumulating elastically in the ice as it's being kind of loaded from the ice stream upstream, and the ice stream is pushing down. So it accumulates, it's stuck there. But at the, I'm frozen again. Oh no.
Or no, you're unfrozen, but
okay. Yeah, I was just saying that the model that I'm showing here just explained it in terms of just elastic strain accumulating in the ice sheet itself, just from being pushed from upstream. The ice is trying to get out. And the frictional properties at the base of the ice stream are constant throughout the entire cycle. I have a couple. So next I'm going to show you the equations, so that might help a little bit to understand. I know there's a lot to take in here. So these are the actual rate and state equations in the red box. And they were originally deduced empirically to fit the experimental observations that I was showing, these velocity steps. They do a really good job at that. And so because of this, these equations have sort of been adopted as the standard description of how friction on faults behaves. So there's 2 equations that you need to determine the friction coefficient. The first equation in this red box gives the friction coefficient mu as a function of the sliding velocity v, and something that's called a state variable theta. And then there's three empirical parameters, A, B, and D sub C. And those have to be determined from the experiments. And then the second equation in this box is the state variable that it has units of time, and it's interpreted as representing the average lifetime of a frictional contact on a sliding surface, but it's kind of like it's a bit abstract. But this state evolution equation basically captures the process of frictional healing during stationary contact. So if the sliding surface isn't moving, it gets stronger the longer it just sits there. So those equations have to be coupled to a description of deformation. And so for analyzing experiments, people use a form of Hooke's law that applies to a rigid block being pulled by a spring. So that's the cartoon on the left. And so the spring is attached to a load point, and that load point moves at a controlled velocity. And so in this model, the block and the spring stands in for the biaxial apparatus. And so the bottom surface of this block is now the experimental sliding surface, and the spring accounts for all the elastic deformation that is occurring in the experimental sample and the apparatus during an experiment. And so now the load point velocity on the spring corresponds to the movement of the center block in the experiment. So these three equations get coupled together, and that gives a model that can reproduce how experiments respond to velocity steps. And so what people do is they do their experiments, and then they take this model and they fit the model to their data, and doing that determines the friction parameters A and B and D sub C. So next I'm going to talk a little bit about what those parameters mean, but one more thing that might kind of help what's going on here is that these three equations can be cast as a nonlinear oscillator equation for the fault sliding velocity. And that kind of concerns the relationship with tidal stresses, because if you add a tidal forcing or an oscillating forcing signal to a nonlinear oscillator, then in general, there'll be a phase lag between the tidal stress and the slider motion because of the nonlinearities. Okay, so I just wanted to show a hypothetical velocity step. So again, the form of a velocity step is that there's the friction coefficient is at a steady state value at some initial velocity. Then the sliding velocity gets increased to a new value. And then there's a spike in the friction, and that's followed by a decay to a new steady state. And so the parameter D sub C is a measure of the amount of sliding that occurs during this decay. Then the parameters A and B, or their difference, determine whether the new friction coefficient is smaller or larger than its previous value. So if B minus A is less than 0, then the fault is said to be velocity strengthening, and that means the friction coefficient gets larger when the fault slides faster. And then vice versa, if B minus A is greater than 0, then we say the fault is velocity weakening, and that just means the slip speeds increase, the friction coefficient decreases. So fault mechanics world puts a lot of importance on this value of B minus A because it determines when unstable fault motion can occur. So velocity weakening materials generally where earthquakes nucleate or start out because it allows for this instability to develop. So when the material is velocity weakening and it starts to slip faster, the friction coefficient decreases, which allows for still further slip speeds and more, and so on. And it's kind of like you get an instability in the fault motion. So that's kind of like super basic rate and state friction. And I've really just scratched the surface. People have been using these equations for 40 years now, and there's a huge amount of data, huge amount of experimental data measuring different friction of different rock types at different temperatures and pressures or in the presence of water. But one thing that all the experiments have in common is that they are focused on faults on the Earth. And so one thing that I'm really interested in doing is working with labs to do these types of experiments for materials or ice that would be found on other worlds or analog materials, I guess. And I think there's a lot of opportunities to do things like that. Okay, so I'm going to move into talking about how faults that obey rate and state friction actually move. So what I actually do in my work is I consider fault as a surface embedded in a two-dimensional linear elastic material. So whereas before the elastic deformation was represented by Hooke's law for that spring slider model, now the elastic deformation has to be determined by solving the 2D elasticity problem. And so that problem gets defined by Hooke's law for an elastic continuum, Laplace's equation for the displacements, and then defining the geometric location of a fault as a discontinuity in the displacement field. And then solving this problem lets you calculate the stress and the displacement field throughout the whole model space as a function of slip on the fault. And so in practice, the two most important things that you can do with that are calculate the change in stress on the fault itself, which is what I need to do the simulations that I do. And then you can also calculate the displacements at the surface, the Earth's surface or the planetary surface, and use that to compare topographical features above a fault to constrain the geometry of a fault. And so I'll show an example of that for the moon in a little bit. But depending on the sense of slip, you can have a little bit of, you have a dip slip fault, which is an in-plane strain problem for thrust faults, or a strike slip fault, which is represented by an anti-plane strain problem. And both of these problems get solved using complex variable methods, which I'm not going to go into, but using complex variables lets you do both of these diagrams here for fault in a half space, which is a good model for faults that are close to the surface. But using complex variables, you can solve more complicated geometries by just finding a conformal map that would transform some geometry you're interested into a half space. So like an elastic strip would be a good model for a fault in an icy shell. And that can be transformed into the half space. Okay, so the solutions for these half space models yield some pretty long and complicated equations, but they can get a somewhat simple solution for a fault in a full space. And that has been used to compute an important length scale called this critical nucleation length. So the critical nucleation length is essentially, gets this term H star in the green box. And it's the minimum length of a fault that needs to slip in order to nucleate an earthquake or an unstable sliding event. So the value of H star depends on both the frictional parameters on the fault and also the elastic parameters of the material that contains the fault. So there's a couple things that are important about this equation. First, the value of B minus A has to be positive. Otherwise, the nucleation length is negative or undefined, and so it doesn't exist. So that implies only velocity weakening faults can nucleate a slip event. And then the second thing is that the total length of the fault needs to be at least as big as this value H star. Otherwise, it's impossible for the slipping patch to become large enough to become unstable. But the one thing to point out though is that this equation comes from analyzing a fault in a full space, and when faults are in a half space, which is the more accurate representation of a fault, then the very shallow regions become more unstable and they need a smaller slipping patch to nucleate an event. And one of the simulations I have has an example of this. Okay, so that's it for all my friction and fault nuts and bolts before I start talking about moonquakes. But I'll just return to this kind of overview slide before I move on. So for any fault in a given location, we can understand its sliding motion by studying these different stresses. So the frictional stress comes from the rate and state equations and doing experiments on the relevant materials. And the elastic stress comes from understanding the geometry of a fault and solving the proper elasticity problem. I didn't talk about the inertial stress, but there are efficient techniques for including that. And then the loading stresses come from the tectonics or the tidal loads. So for moonquakes, I'm going to go over some previous work that has determined a lot of this information that's necessary to do the simulations. And then I'll show you my demo in simulations. Okay, so moonquakes, and I'm really interested in shallow moonquakes. I'm going to go over some background material and kind of go through this as a sort of like a sketch for a proposal that I want to write. So from 1969 to 1977, there were 4 seismometers on the moon. And so the cartoon here is showing those seismometers locations as the open squares. And then the open and filled circles in the cartoon show the relative locations of the shallow and deep quakes that were recorded. So the seismometers recorded 28 shallow events, and these had magnitudes from between 1.5 to 5, and a few had estimated stress drops of over 100 megapascals. So that's how much stress is released by the event, and that's quite large. So the stress drop doesn't necessarily correspond to the spatial size of an event, but for comparison, the Tohoku earthquake in Japan in 2011 had the stress drop estimates for that event are about 20 megapascals. And so some recent work has located about 17 of these shallow events right at the moon's surface using some like special seismological techniques for sparse seismic networks. And there's some indication that those events are triggered by tidal stresses. So I also, before I move on, want to mention some aspects of the deep moonquakes because they're very mysterious. The seismometer network recorded more than 7,000 of those events at depths between 700 and 1,200 kilometers and with magnitudes of about 3. And those also appear to be triggered or at least modulated by tidal stresses, which is very, very curious because the estimates for the tidal stresses at those depths are in the neighborhood of 100 kilopascals, but the confining pressure at those depths is in the neighborhood of 3 gigapascals. So it's hard to understand how such a small tidal stress is influencing something feeling such a large confining stress. And there are similar deep earthquakes on the Earth, but those are generally associated with metamorphic dehydration reactions, which doesn't seem like a good explanation for deep moonquakes because there shouldn't be any water around. Okay, so the rest of the background that I have is from these 3 papers that I just wanted to acknowledge because a lot of work went into these 3 papers, and it gives me a lot of the information that I need for these simulations that I've shown. And Catherine Johnson and his works at PSI was one of the contributing authors for the bottom paper. Okay, so there are thrust faults all over the lunar surface, and there's more than 3,000 of what people call lobate thrust fault scarps that have been identified from the Lunar Reconnaissance Orbiter Camera. And so this map is showing the location of the fault scarps in red and shallow moonquake locations as blue circles. And the seismometers are shown as black diamonds, but they're kind of hard to see. There's 2 on the left edge of the map, and then there's 2 right next to each other on the right edge. And the mare are shown in tan. So one thing to notice here is that the faults are mostly in the lunar highlands. The individual fault scarps have about tens of meters of relief on them, and they're about 10 to 20 kilometers long, and they also form in groups or clusters that can be several hundred kilometers long. And another interesting fact about them is that they appear to be less than 50 million years old based on the infilling rates of troughs or grapens that are associated with the scarps. And so the best explanation is that how they formed is that is due to recent or maybe ongoing thermal contraction of the moon. And so another important fact about these faults is that the orientation of the scarps is best explained by the tidal stress field on the lunar surface. So if the faults formed under the influence of just a thermal contraction, it would be an isotropic stress field and their orientation should be random, but that's not what's observed. So the top left map is the map I just showed, and the bottom left is showing the black double arrows show the average orientation of the scarps, and the red bars show their expected orientations if they form due to thermal contraction plus orbital recession stresses and also diurnal tidal stresses at apogee. So where those lines, the red and black lines overlap, is where the faults have formed in the expected orientation. And you can see that they don't all agree, but a lot of them do agree, and significantly more than would be expected if the orientations were random. So on the right plot is showing the same thing. The x-axis is the angle between the expected and observed faults, and the blue line is for a simulated population of random faults. And the other lines are stress models that include the tidal influences. And so all the tidal models do a better job at explaining the fault orientations than the random population. The main point is that the global orientations of the fault scarps are best explained by including tidal stresses. And so if the shallow moonquakes are occurring there, then the tidal stresses are an important component for causing those events. And so another line of evidence there is that there's a statistically significant effect of the tidal stresses on the timing of the shallow quakes. So this plot is now showing the, it's called a demodulation ratio of the moon's EDM during the time when the seismometers were active. And so the red dots are times when the shallow quakes occurred. And so the important point of this plot is that 18 of the 28 shallow moonquakes occurred when the moon was within 15,000 kilometers of apogee. So the authors of this study, Waters et al., they did a statistical analysis by generating 10,000 sets of 28 random events. And then they found a 1% probability that 18 events occurred in the way that they were actually observed. So that indicates a real relationship with the tidal stress that isn't an artifact of the small sample size. So that gets back to what I was saying before about a tidally driven fault being like a nonlinear oscillator. It's not necessarily the case that the slip should occur during the peak tidal compressive stress. It could be correlated with the stressing rate, for example. Okay, so what do the fault scarps actually look like? And what is the geometry of the faults beneath the scarps? So I'm going to show an example from this crater, Mandelstam crater, which is, I've marked the location of the crater with a yellow circle on the map on the right. And then then the white arrow on the left shows where one of these fault scarps is. So on the right now, you're seeing a DTM of one of the scarps, and it's superimposed in the local topography. So you see it as a wavy black line that occurs on the downsloping wall of the crater. And I also want to say a little bit about using the topography of the fault scarp to constrain the orientation of the fault that's beneath it. So first, the local elevation has to be detrended from the topography of the scarp. So on the left now, you're seeing the detrended scarp elevation on the upper half of that plot, and that corresponds to the profile along the white line on the right image. And then the lower half on the left image is showing the assumed fault geometry that can use to be model the uplift of the scarp itself. The process is to assume that there is a thrust fault that dips beneath the scarp and the fault reaches a depth T, and also assume that there is some slip distribution S on the fault, and that that slip peaks in the middle of the fault and tapers to 0 at the endpoints. And then use the solution for the fault, the elasticity solution for a fault in a half space, and compute the surface displacement that gets induced by how much slip you assumed on the fault. And then the process is to fit that to the observed scarp topography to constrain the fault geometry. So the top right is now showing an example of one of these fits, which is a good fit. Between these two papers, Williams et al. And Waters et al., they fit 7 different scarps, and they found that slips on the faults are about 18 to 110 meters, and dip angles are between 35 and 40 degrees. And these faults reach depths of about 250 to 900 meters. And there's some discussion in the Williams et al. Paper about what were the proper values for the elastic constants in the lunar surface. And they used a value of 40 gigapascals for Young's modulus and a 0.25 for the Poisson ratio. I always think about shear modulus instead of Young's modulus. So these values give you a 16 gigapascal shear modulus. And so there was a discussion about whether these elastic constants should be 10 to 100 times smaller, possibly because of the heavy impact damage in the lunar crust. And they found that the value didn't really affect their fits. Because when you're doing these kind of fits, the main control on the topography is how much slip is on the fault. But all things being equal, you could reduce the elastic constants by an order of magnitude and still get basically the same fit to the topography. But you would get larger stresses in the material around the fault. So if you reduce the elastic constants by an order of magnitude, the predicted topography is the same, but stress induced by the slip on the fault is an order of magnitude smaller. And that effect actually has a huge influence on the fault simulations of the fault motion, which is what I focused on for these two demo. I did 2 demo simulations for you. So here's how I set these simulations up. They have identical geometries and loading conditions and frictional properties. And the only thing I changed was I did one simulation with a 16 GPa shear modulus and one with a 1.6 GPa shear modulus. And so I chose a dip of 35 degrees and a depth of 700 meters. And so that gives them a long dip fault length of about 1,220 meters. And I used a very simple loading for this fault. Simulations don't include the tidal stresses or an isotropic thermal contraction stress because all of my codes right now are set up to do subduction zone simulations. So I apply constant slip rate at the lower boundary of the fault at that red dot in the cartoon. And that's a proper boundary condition for a subduction zone because in subduction zone, the fault is sliding at a constant rate at depths where earthquakes occur, or depths below where earthquakes occur. So I just assume that 100 meters of slip occurs on the fault over its 50 million year lifetime. And that gives you a sliding rate of 10 to the negative 13 meters per second. So for context, tectonic plates on Earth are moving at a rate of about 10 to the negative 9 meters per second. Okay, so that's how the loading and geometry is set up. And I was actually able to find one experimental study that's relevant to the moon, this paper, Frictional Properties of Anorthite, which is a very common mineral in the lunar crust. Most of the experiments in this paper were at really high temperatures and high normal stresses. And the coldest one they did was at room temperature. So I'm just using the data from that one room temperature experiment they did to calculate the nucleation length that I was talking about before. So because the nucleation length depends on the shear modulus, the 16 GPa simulation has a nucleation length that's larger than the fault length. So as I was saying, if this fault were in a full space, it wouldn't generate any moonquakes, but in this simulation it does because the shallow part is more unstable. And then in the second simulation, the nucleation length is about an order of magnitude smaller than the fault length. And so the fault generates quakes in a different way. Okay, so this is the first, this is a short video of the first simulation. So the top panel is showing the fault geometry. Depth is on the y-axis in meters. Distance is on the x-axis in meters. And the fault is shown in red. And then the bottom panel is showing the slip velocity in meters per second along the fault. And so when I play the movie, the fault will change from red to blue when the slip speeds get above a millimeter per second. And in the middle, you'll see how much time has passed during the model run. So it starts off with this kind of slow pulse going up, and then it hits the surface and it nucleates this moonquake, which then propagates back down the fault till it hits the bottom boundary. And then it goes into a cycle and it does it again. So there's the second event. And this simulation produced 2 events in about 3,700 years. And each event caused about 7 millimeters of slip on that fault. Now the second simulation, and again, the only difference is that I changed the shear modulus. I made it smaller. And so again, it starts with a pulse going up, but then that pulse destabilizes itself here and then nucleates the moonquake, which then propagates both directions. The whole fault slips and then it stops slipping and it goes back into a cycle again and makes another event. And so this simulation takes a bit over 18,000 years to produce 2 events. And the events are larger in terms of slip because each one produces 4 centimeters per event. So here are just two plots comparing the 2 simulations. So the upper panel shows the maximum slip velocity on the fault through time. And so each spike in this plot is a moonquake. And so you can see when the shear modulus is lower, the blue line, there are less events, but the slip speeds are almost 2 orders of magnitude faster. So they are kind of, in a way, larger events. And then you see a similar thing on the bottom plot, which shows that this bottom plot is showing the cumulative slip that occurs on the upper surface of the fault. So when the shear modulus is high, there's more frequent events that are causing less slip. But even though they're causing less slip, they're actually larger magnitude because the magnitude depends on the shear modulus as well. And the difference in the shear modulus gives you a larger magnitude. So they might actually be releasing more energy. So the main point about these simulations is that the shear modulus has a very strong effect on the model behavior, and also that the sliding behavior can be quite complex. And I don't think it's too wise to read too much into these simulations because they, as I said, the loading conditions aren't set up properly. But I think they're good motivation for doing more work. So this is kind of like my conclusion slide, but it's really just points, things that I'm interested in doing. And so first, I'm really interested in doing more friction experiments on anorthite. And I also had an idea that it would be interesting to do experiments on regolith simulants. So there's companies that sell granular rock mixtures that are intended to reproduce lunar regolith. And so I think it could be instructive to get some of this material and do friction experiments on it and do those experiments at the appropriate temperatures and pressures for the moon's surface. And second, as I mentioned, these simulations I just showed don't have the proper loading characteristics. So new simulations need to have this worked out correctly for the shallow lunar faults. And I had a really nice conversation with Matt Walker at PSI a couple months ago about working together on doing that. And so that would be really exciting. And last, it's important to think about how to constrain the simulation. So I've been considering doing like a very large number of simulations to do statistical analysis of the model data and try to think about how the timing and the size of the events and the location of the events depends on the tidal stresses and also the frictional properties. But those are all things that would be great to hear opinions on. So my last slide, a colleague of mine at Vermont, Mahi Zaman, he's a grad student. He's been doing really cool ice friction experiments, and he's going to be presenting at PsyCon in a few weeks. He's been doing experiments on pure ice and also ice with a 3 weight % ammonia content at temperatures down to about -175. And so he's been getting some really cool data. And eventually we're going to work together to incorporate his ice friction data into models of icy fault motion on Europa and Enceladus. So please check his presentation out. You're going to be at the conference. Okay, that's my talk.
Oh, thank you very much, Rob. They're very, very interesting. You could do Pluto too, you know.
I know. I was reading I read the review paper of its geology recently, and I was just blown away. I mean, there must be faults everywhere.
Yeah, it's really spectacular in that regard.
Yeah.
Any questions for Rob? Go ahead and unmute and chime in.
Hey, Rob, this is Dave Vanneman. I remember hearing that in the with the Apollo drill core, the one that went meters into the regolith, the astronauts hated it because the thing would kick like a mule. Some of them were actually slightly wounded, but I think they pinned down the problem to it was tested at atmosphere in loose regolith simulant, but not in vacuum.
Right.
And the implication was that atmosphere acts as a lubricating fluid. Now that's porous media, so I know it's a completely different setup, but does vacuum have any effect on your experimental work?
Yeah, I think it actually will have a huge effect because maybe about 20 years ago, some people did a friction experiment in a biax, like I was showing, and they put like a special chamber around their sample and they filled it with desiccant to drive the relative humidity down. And they found that had a huge effect on the friction response, because I guess like water in the atmosphere was kind of helping this surface, you know, when the frictional surface isn't moving, it's healing. And that's where they saw the biggest correlation with the humidity. So I think that doing the experiments in the vacuum will have a very strong effect on the response, and there are machines that we can do that with. So I didn't mention I was going to mention that, and then I decided not to. But yeah, thank you.
Hey, Rob, I'm actually an astronomer, so this is very far afield from what I do, but I'm really curious about those deep moonquakes, and I was wondering if you had any thoughts on other hypotheses of what might be causing them, since the tidal stresses are so low.
Right. So on Earth, there's kind of similar events called low slip events, and the going theory is that the effective stress on the fault where those events are is low because the fluid pressure is high. So maybe there's I'm not very familiar with the lunar mantle, but maybe there could be some partial melt lubricating the faults or sliding surfaces where those events are taking place, because there shouldn't be any water coming out of the rocks, right?
Yeah.
I really don't know.
Would that melt come from impacts or from just simply tidal stresses, low tidal stresses?
Oh, I don't know. Yeah, maybe there's some tidal heating that's causing like a partial melt. I don't know enough about how that works.
From heat formation, you know, having not having escaped the entirety of the moon's depths over the age of the solar system.
Okay.
Or the age of the moon, at least. You know, these depths. What do these depths mean, and are there like error bars associated with them?
Yeah, I don't know exactly how
associated with them.
What was that?
Or scale lengths or something associated with them, like
right.
The endpoint of something, and it would extend to something longer or whatever.
Yeah, right. I feel like the locations might not be that well constrained because there's only 4 seismometers, but the depth range was like over a few hundred kilometers. So I think their locations have been reanalyzed recently with like machine learning techniques that can do a pretty good, at least within 100 kilometers accuracy. So I think I felt comfortable with when I read those papers where they tried to relocate them with the, but of course more seismometers would be needed to get it really precise.
Yeah, I mean, how many decades have we been talking about, lunar seismic network? It's like, what's the problem with that?
I don't know.
Uh,
I mean,
I think it wouldn't be too difficult to just drop a bunch of crap around the surface of the moon, so.
Yeah, the seismometers are pretty small these days.
Yeah.
I have a question, probably geophysically speaking, this is a naive question. In the equations that you described, I didn't see gravity mentioned. So if you look at an object, say 1,000 kilometers versus few tens of kilometer size, will the gravity or the gravity differential make any difference?
You mean the change in gravity from over the length of the fault?
For example,
Or just
when you're talking about the moons, the large moons versus a smaller object, will there be any differences in the faults, for example, due to its size?
Okay, yeah, I think the main difference would just be the resulting stress that the fault feels from the material sitting on top of it, and that stress depending on the gravity, because of the kind of the normal stress that a fault feels has a large influence on its motion and also on the frictional properties. I think that would probably be the main influence.
Okay, thank you.
Think about it more. I could probably come up with some other points, but.
Any other questions for Rob? Well, Rob, I want to thank you again. It was a real interesting, seminar, interesting topic. It's kind of like whenever you get presented with these things, it's like, why aren't we doing more? So,
well, thank you for all listening, and yeah, I hope it was informative, and I hope I get a chance to talk your ears off about friction, because it could go on for all day, really.
Great.
Thanks again.
Okay, thank you.
Bye.